All right, so think about all the mistakes you've made in your life. And that's where we're going to start with percent error. Now, listen, I know a lot of you have a long, long list of things that you're thinking about right now. And some of you have a very short list, I'm sure. Right? Just perfect. You're a student. I know, a lot of you are out, except when you're pointing to yourself, that's a mistake, because that is not humility. So, sorry. It's a grave error. No. So think about the mistakes you've made. Some of them are little mistakes. Some of them are really big mistakes. Think about a science exam. If you get 1 mark off out of 10, that means you were pretty close to having the complete right answer, right? You got 90% of the question correct or so. But if you got 1 out of 10, that means you were way off. Whatever you wrote down, if it was anything at all, was from a completely different universe, right? Or it was in a language that the teacher couldn't understand and had nothing to do with science, or whatever it was. So the concept here, percent error, is an indication of how far off our measurements are to the true and accepted real value. So for example, if we do some kind of experiment on the density of water, let's say, and we know under these conditions the density of water should be such and such, and we do an experiment, and in our experiment what we're trying to find is the density of the water in the sample, and our measurement does not agree with the true and accepted measurement, we would say that in our experiment there was some degree of error, and we would call it percent error. So in this class, perhaps we might get to an experiment where we're going to deal with this in Chemistry 30 for sure. There's experiments where we ask you to calculate your percent error. So if we are creating or generating a precipitate from the mixture of two solutions, and you filter that precipitate out, you let it dry overnight, and then you weigh it. Your calculations, you would do your calculations, and you would figure out, hey, this is what I should get. So this would be like the accepted value based on the rules of chemistry and stoichiometry, which you haven't learned about yet. But based on those rules, I should get this much if it's 100% efficient. But you got a different amount. So I would ask you, calculate your percent error. And you would have some kind of indication of how off you were, right? How big an error that you experienced in that particular lab. So percent error, and I'll let you fill in your blanks here on your paper and your notes, is the measured value. Okay, first of all, these straight lines are there for a purpose. Those are absolute value signs, okay? They're absolute value. So we generally deal with absolute value. There are cases where we would state a sign, a positive or negative, in front of the percent error, and I'll talk about that. I'll talk about that as we go through this lesson. But generally, the percent error is just how much off of the anticipated value are you. So you take the measured value minus the accepted value, and really because it's absolute value, it doesn't really matter which one you write first, honestly, because it's absolute value. So if you get a negative answer, you're going to change it to positive anyways. But what's really important that you remember is that you always divide it by the accepted value, okay? So on the bottom is always the accepted value, and that's where students go wrong. They divide it by their measured value, but that's actually going to be different because your measured value is different than the accepted value, so your percent error might be slightly off, okay? So it's the difference between the measured and the accepted or published value divided by the accepted or published value, and then times 100. So that gives you the percent. Okay, so it's kind of like in a test, right? If you get 89 out of 100, right? Your measured value is 89. The accepted is 100, right? So divided by the accepted, so that's 11 out of 100 times 100. That's 11% error. If you got 89% correct, you got 11% incorrect. So that's what this is stating. Got a couple questions? Yeah. Okay, so is the percent error higher or lower? That's the question. That's where we might use like signs on the error. Okay, so sometimes you'll get a higher value than the accepted value, so you will have a percent error, and you'll have to use other information in the question to state whether it's higher or lower. Sometimes you might say plus 0.2% error, or minus 2.5% error, and that would indicate whether your measurement is above or below. So generally speaking, it's a It's an absolute value, but if we do use the signs, that would indicate where your measured value is. If it's above, too high, or if it's too low. And we'll do an example like that here today. Okay, good question. Any other questions? Okay, all right. So let's do our first example, and you'll have to write the details down here, and I'll jot down the givens here as well. So remember, when you're answering a question or doing a calculation in class, write down your givens, right? I think, do you guys learn GUFs with Mr. Reed? You guys learned that yet? Anyways, write down your givens, okay? Write down what you're trying to find. Write down any formulas that connect those two, and then solve, okay? So that's generally givens. You write down what the unknown is, so that's where the GUFs come from. Givens, and this is kind of Mr. Reed's thing, so he teaches this all the time, so I assume that some of you guys know this, but write down your givens, state the givens, understand what the givens are, okay? What are your unknowns? So this is what you're trying to solve for. It's usually just one thing, okay? What are the formulas that relate the two? Formula or formulas that required, and then solve. So use your givens and your formulas to solve for your unknown. Okay, so that's where GUFs come from. So feel free to have that as a bit of a template. Okay? All right, so what are the givens? Density of water is at 4 degrees is known to be this value right here. So the accepted value, okay, this is accepted, is 1.00 grams per milliliter. All right, does everyone understand that this is the accepted value here? The density of water is known to be. There we go, that's our accepted value. Now, this 4 degrees, I'll talk about this 4 degrees in a bit, but this is just the density of water at 4 degrees. This is the situation we're talking about. So this 4 degrees is not a measured value in a sense, okay? So we don't have to worry about sig figs for this one. This is just part of the description of the situation. All right, so 1.00, okay? Notice there's 3 sig figs here. Right? 3 sig figs. I'm just going to take note of that in that measurement. Kayla experimentally found the density of water to be. Okay, so experimentally found. So that's going to be the measured value, and this is her measured value. So let's jot that one down. Measured value is 1.075 grams per milliliter. And this has, of course, 4 sig figs. I'm just going to note that as well. So what should my answer have? This is all that I'm given. If I do any multiplication or division at all, what should my answer have as far as precision? How many sig figs? Yeah, the answer should have 3 sig figs. The lowest number between here, 4 and 3. Okay? This 4 degrees, don't say, oh, there's only 1 sig fig there. Well, this is not a measured value. This is just a statement of the situation. So we're not going to count that as a measured value. This is a tried, true, measured value. Precision is included in there. This is a measured value. Precision is included in those digits as well. So we're going to do 3 sig figs, okay? All right, so let's bring back our formula here into view. So the percent error is what we're looking for. So percent error is the absolute value of the measured 1.075. And you don't have to use your units in here in the formula, of course. As long as your units are the same, you're good to go. Minus 1.00. Now, which number do I put on the bottom? 1.00. Good, good. Okay, close that with an absolute value sign there. And then times 100. Okay, so we want percent. That's why we do times 100. All right. So it looks like the difference here is 0.075, right, when you subtract those. And if it's positive or negative, it doesn't matter because the absolute value signs are going to make everything positive here. So I'm not writing the absolute value signs because I don't need them anymore. I know that this is positive, so times 100. And it looks like the percent error here is 7.5. And I can state my answer to 3 sig figs, so I will throw a 0 in there to add that, to note that precision. So percent error is 7.5%. Okay? All right, so any questions? Any questions on that one? I'm thinking it should be pretty straightforward. You got a formula, plug your stuff in there. Make sure your units line up, check your sig figs. Let's do another one. Okay, so here's another example. Take you You don't have to copy this down. Like I say, you can just write down the givens with me here. So what would the givens look like here? An object has a mass of 35 grams. Has a mass of 35 grams. Anthony's balance weighs 34.85 grams. So which one of these do you think would be the accepted value? Yeah, not the one that Anthony measures or that he weighs out, but it has a mass of 35. It's known to have a mass of 35.0 grams. So that would be your accepted. The measured would be Anthony's measurement here, which is 34.85 grams. 3 sig figs, 4 sig figs. Answer is going to have 3 sig figs. So we'll just make a little note of that. What is the percent error of his balance? Okay, so obviously his balance is off a little bit if this known weight is 35.0 grams. He did not get 35.0 grams. He got something different. So percent error equals absolute value of measured is 34.85 minus 35.0. And again, it really doesn't matter which number you put first. You're just finding the difference, the absolute value of the difference. And we put 35.0 on the bottom, don't we? Right, because that is the accepted value. So always the accepted underneath. That's where students go wrong there. Okay, so this is what? 0.15? It's actually, here, I'll just show this step too. So you're going to get, if you do this on your calculator, you're going to get negative 0.15. And this is where we have to remember that the absolute value negates or gets rid of all the negative value inside there. So this is actually just positive, really, 0.15 over 35 times 100. So let's do that on our calculators there. 0.15 divided by 35 times 100. And of course, multiplying by 100, you just move the decimal place over 2 times. So this is our percent error, okay? So 0.15 out of 35, that's not a lot, right? That's a very small amount out of a very large amount. So you're going to get a very small percent error. Now, did anyone else get that? Did I punch all my buttons in correctly? 0.42857. So 0.42857. And how many sig figs am I supposed to have? 3. So let's round this to the 3rd sig fig here. I look at the 8. I look at the number to the right of it. It is a 5. So I have to bump that 8 up to 9. Make sure you include your units. So that's percent, whatever, your percent error. Okay, any problems with that? Questions? Concerns? So who is more accurate? Which situation was more accurate? Yeah, this second one. Look at 7.5% is much bigger than 0.429%. And here's the question I get a lot from my students. What's a good percent error? What's acceptable? That's a tough one. It's kind of like the lower the better, really, right? The smaller the percent error is the better. So it's kind of like if you have 7% error versus 0.4% error, the 0.4% error is much more accurate. So what's good? It kind of depends, right? If you're making an estimation of, the distance from the Earth to the Sun, right? Obviously, if you have a large percent error, that's a large number of kilometers. But it's the same sort of proportion error as if you were just measuring, the length of your pencil, right? If you had 7% error, the distance between here and the Sun, that's millions of kilometers, right? But if you had 7% error measuring the pencil, it's probably just millimeters. So what's a good percent? The lowest possible, okay? That's a tough question. Generally in labs, if you have under 10% error, you're okay. Under 5 would be best. But sometimes things go haywire, and I've had students with 30, 40, 50, 70% error. I'm like, really? What happened? 70% error, oh my goodness. So yeah, there's problems. But if that happens in the lab, don't worry too much about it. Obviously, you did something wrong, right? Or something happened. So you just have to figure out kind of what that could have been and comment on that in your lab report. It's not always possible to be doing the lab over again. Say, I got 70% error. This is a disaster. You can't always do your lab over again. You would probably want to do your lab over again, right? If you got 70% error. But in our high school labs, something went wrong. It's your job to figure out what might have gone wrong and to comment on that in the sources of error section. Okay, so just a note if that ever happens. All right, I think this is the last example that I have for you. So it says this: Shelby measured the volume of a cylinder and determined it to be 54.5 centimeters. Okay, so we've got measured is 54.5 cubic centimeters. Awesome. The teacher told her that she was 4.25% too high in her determination of the volume. Oh, so this is a bit of a different kind of question. They're giving you now the percent error, and you're asked to find the actual volume. So accepted is unknown. That's our unknown. And percent error is 4.25%. That's exactly right. So we'll jot some of that stuff down, and then we're going to get ourselves ready to find a formula that connects these. And of course, our percent error formula is the only one we're working with here today. I'll change colors here. So this is where maybe the positive negative comes into play. I'll tell you how I would deal with this one. I would write 4.25 here on this side where the percent error should be in our formula. Now the absolute value signs, okay, this is what I would do. You want to note that the measured is too high. This is high. Her measurement she's too high. So accepted value is lower than measured, okay? Now, if I know this, I can just go ahead and leave this as a regular plus 4.25. And what I'm going to do is on top here, I'm going to put the larger quantity first, and I'm going to subtract from it the smaller quantity. Then I don't have to worry about the absolute value, okay? So always put the larger one, if it's the measured, or it doesn't matter. The large, what does that say? Larger one, I don't know what large is. The larger one first, because we're going to leave this as a positive, and this is going to be positive. That will make this positive. So is the larger one her measurement or the accepted? It's her measurement, right? Okay, so we'll put 54.5 there. Now the accepted value is unknown, so we got to put an A right here. I'll get to your question in a second. And an A right here. Okay? And then times the 100 over here. Yeah, good question. So when the percent error is positive, if it's too high, you put the larger one first. If it would be too low, okay, if it's too low, watch this. This is what I would do. I would put the negative here then, and then you would put, you would switch these around, I guess. You could, whatever. Or you could just leave it like this and, just understand that you would put the larger, I would just switch these around and you kind of know. So mathematically, you got to use your head here too. So I would just say, you know what, here's our error. This is the larger one. I'm going to solve for A, and it's going to turn out to be smaller here because of the way I've set this up. So it's kind of not a very direct question, or answer for your question, but okay. So let's divide by 100 first. Let's get rid of 100 here because this should be a decimal, right? So this is going to be 0.0425. Then we're going to have this over here. And we have A in two different spots. So, okay, first thing you don't want to do, don't do this. Oh, the A's are gone. I've got 0.0425 equals 54.5 minus. No, that doesn't work. You can't do that in math, just for those of you that are wondering, okay? What we want to do here probably is get rid of the denominator A. So I'm going to multiply both sides by A. And again, I'm showing you every step so that you can do this very methodically so that you don't make any mistakes. And this is the way I teach math, right? So you show your steps and you don't make any mistakes and you're confident about your answer. So we get rid of the A in the denominator. That's really nice because now we have like terms that we can gather. So for those of you that are, whizzes at math, you would say, okay, here's an A term and there's an A term. Let's get those together because I need to solve for A. So I'm going to add A to both sides. And that's 1A, right? I'm adding 1A to both sides. 1A. So this might look a little strange because really this is understood to be minus 1A, so I'm adding 1A, which means that over here on the left, this is 1 plus 0.0425 a, or 1.0425 a equals 54.5. And let me know if that disturbs you, if that's troubling for you. We okay? Don't be shy. There's something you need to ask me about. When I put the ones in here, maybe it looks a little funny, but we want to gather the like terms, so bring all of the a terms over to the same side. All right, I'll keep going then. So now we divide by what? What do I want to divide by to isolate for a here? Exactly. Very good. Yeah, question?
Wait, what happened to the 1a on the left side?
Okay, what happened to the 1a on the left side? The 1a I combined with this 0.0425a. So I just added them. So that's 1.0000, whatever, plus 0.0425a. I have 1.0425a. I've combined these two together. 1 plus 0.0425. That make sense? Good? All right. Okay, good. Let's be clear. Yeah, any other questions?
Is the 2A's? Isn't the 2A's that you're adding together?
I want to make sure you're on the same page, so that's good. All right, so now let's finish this calculation, and so that means I'm going to do, I'll turn this on. I'm going to do 54.5 divided by 1.0425. 52.278. Okay, 52.278. Now I got to take a look at my sig figs, and I have to make sure that this accepted value is, what did I have to say? Lower than the measured. Oh, here's the measured 54, 52. Okay, real good. Sig figs, 3 sig figs. So my answer then is going to be 52.3, and what was it again? Centimeters cubed. Okay, for the accepted value. All right, so is that okay? Any questions about that there? Any further clarification? You guys are pretty good? All right. Okay, what I'll get you to do then is to look at your worksheets, and I'm just trying to find your percent error worksheet here somewhere. Yeah, the alternate assignment. So you guys have the alternate one there. So there should be your first question. And I won't show you all the answers just yet. But you guys can get started on that. You have 4 questions there. Okay, any final questions from this percent error lesson here? Because I'll get you to... Good?